our meeting. And so the sunlight hour is independent to the radiant. So I guess it should not be
I'm sorry that I interrupt you. Someone has sent a message in the Slack groups. I think that he or she cannot join the group.
Let's see. Yeah, thank you. Okay, I cannot join the meeting. Could you send the link to me? I guess I already sent it. Let's share this to the workshop. Thank you to remind me. We're still missing someone.
No problem.
Thank you.
All right, you are in now, so we move on. Let's continue. So the evaluation is about how you not just the performance of the design, but also how you consider this design is satisfy some basic constraint from the architecture perspective. So here we first, but we still need to first to evaluate the performance. For example, in here we have this building as our target building, and we are using the sunlight hour on the facade surface to do the evaluation. So if you are still using the one that connect the roof, you can just make another BREP and connect the exterior surface and interior surface with this BREP, and do not connect the roof surface, and then and connect this BREP to the geometry of this simulation component. And I also increase the grid size here. The original grid size I said is free, but it's maybe provide more precise simulation. But since we are start going to run the optimization, so we can still reduce the precisions of the simulation and to speed up the whole optimization process. So I change here to the 5. So you can save us a little more time in the optimization process. So if you, let's say, to change the geometry, you can see that basically the result of the simulation can be produced instantly when you change the geometry of the design. All right, so in here we are, because we cannot evaluate the design the piece, each of the facade surface. So you usually just consider the overall performance of the design. So here we use the result. The result here is actually the sunlight hour of all the analyzed point in the surface of the facade surface on this building. So you can see that some of them have like a 7 hour and some of them have a 0 hour. So they usually have 2 ways to do the evaluation of the performance. We can use the massive addition here. So we just accumulate all the sunlight hour on this facade to get a result that to indicate the overall performance of the building design. Or we can also use like an average. Average, yeah. So the average, just as I said, they will provide you the average sunlight hour on the facade surface. But just keep in mind that using the average may have some problem if for the optimization process, because let's say that you are setting a design have like 10,000 square meter, and they will have let's say like 10,000 or even 20,000 square meter on the facade surface. So if you're using the, if you can keep the facade area similar during the whole design optimization process, it is okay. You can use the average. But however, if sometimes they are certainly have a very small design that have a very good average sunlight hour, in that case, they will have to like introduce some kinds of the bias on the performance evaluation, because this building is very small. So they maybe have some advantage to get more sunlight accessibility than the building with a larger volume. However, this kind of design is actually not feasible to be used. So in that case, if you're using the average method, the real number or the overall sunlight hour of the whole building cannot be evaluated by the average number. So in that case, you might need to use the mass addition. So in that case, if the building is very small, even though they have some advantage in the sunlight accessibility, but they only have a very small number or a small facade surface area. So the accumulation of the overall sunlight hour of the whole design will be still very small. So in that case, it won't introduce the bias to the performance evaluation. But if the design is just like a very stable in terms of the facade area or the some kinds of the feature or the attributes you are looking at, it is okay to use the average method. But in this case, we're still using the mass addition method to do the performance evaluation of the building. And since we got this value, so this is the first part, and the other part is about how we evaluate the feasibility of the building design. So in this case, we are using like the gross area of the building. So here we can get the gross area of the buildings. Let's say we just say that like here is the 18,000 square meter of this building. So maybe we can set a number like 15. Let's have so here we are using the target gross area constraint to ensure that all the design generated design can have a very close gross area to the target gross area. However, because there are sometimes some weird combination of the parameter can still create some design that cannot make the component cannot find a solution that close to the target gross area. So in that, so to prevent this design to bring some infeasible design to the design population, so we need to using some like a punishment penalty function in the fitness evaluation to exclude this kind of the design. So in here we can say that, let's say here is we first kept the gross area of the generated building design, and we're using here like a penalty function to punish the design that cannot have a satisfying gross area. So here because we are using like 15,000 square meters, so we also change here is to the 15. And you can see this function is basically means that we calculate the difference between the x and the y. The x is the actual gross area of the generated building design, and the y is the target gross area we set, and divided by the y, so we can get the relative value between how small or how large between the target gross area and the actual gross area. And in this case, because let's say that we want to maximize the sunlight hour of the winter, let's change here. We delete this one. We connect here is the overall sunlight hours. We connect our overall sunlight hour to this multiplication component to multiply the sunlight hour to the penalty function. Because what we want to in this case we want to maximize the sunlight hour. So in that case, if the building is not satisfied the target gross area constraint, we need to scale down the value of the sunlight hour. So in that case, we need to multiply a number smaller than 1 to scale down the overall sunlight hour here. So here you can just change here to 1, subtract this bunch of the calculation, and then can get the punishment function. So we can see that they usually have they are always numbers smaller than 1. So it means that they can to do some punishment on the overall sunlight hour if the design have a very large gap between the gross area. So let's change another one to see how this will change. So we can see that this one have only like almost like a 16,000 square meters. So we can see that this punishment will become a little bit larger. So you can see that using this way, we can include some more functionality evaluation or the assessment into the evaluation of the overall evaluation of this design, because no matter how well this design can perform in terms of the sunlight hour, if the building cannot satisfy the functionality functional requirement, that this design is still infeasible to be used in the future design development. And so another way to do so is we can also using a little bit more interesting way to do the punishment function. So we can use the graph method and create a graph type like a result. So we are just trying to mimic the in the machine learning, you maybe know a function called the sigmoid function. So we are also trying to mimic the sigmoid function here. We can connect it to this output to this here. So we can see the output will be at here. And in that case, we can use this the value produced by this graph method as the punishment function. The reason we're using that because we see that if the actual difference between the target gross area and the actual gross area is small, this curve at this area is basically flat. So it means that we see that this building is let's say that is acceptable to have this kind of the small gap. So we want to have a very harsh punishment on the design with this gross area number. So basically the punishment is very close to 1. And you can see here, this will make the punishment very small. But let's say that we disable the target gross area constraint and to generate a design a little bit more infeasible. Let's say this one we set a 15, but this one have a 24. So it should have a very strong punishment on the evaluation. So we can see this line comes to here. So even if we're using this function to calculate the punishment, they still have like a 0.37. But if we're using like this sigmoid function, you can see they will have a more harsh punishment on the fitness of the design. So in this way, we can try to preserve the design have very close gross area differences between the target gross area and the actual gross area. But if the design reach to this region, their fitness will be decreased very fast. So in this case, no matter how well the performance of the design, we do not see that this building should be keep within the design population and to give them the chance or the opportunity to be survive in the following design evolutionary process. So let's generate another one to see whether. So you can see that in this one, they can still have acquire a very harsh punishment on the design because this already have like 2,500 differences between the gross area. So I guess so. I think this is the basic about how to using this kind of the soft constraint in the fitness evaluation to preserve the design have okay or the acceptable feasibility, but also exclude the design that cannot satisfy our other functional or architecture design requirement. But another thing you should be careful is that if you are setting the objective of the organization, let's say to minimize the solar irradiation in the summer, you need to first, if you using this method, you need to change the this from the subtraction to the addition, because in that case, if we want to minimize some value, the punishment should be enlarged or scale up the original performance evaluation value. So, and for this case, you also need to, let's say, to change here the y-axis from 1 to 2 maybe, to make the punishment value become a value larger than 1, is not smaller than 1. So this is something you need to careful when you're using the punishment function. So here is about the design evaluation part. So we can go to the last part of the using the optimization. Here is the how to define the optimization algorithm. So when you double click this component, there we have a dialog box popped up, and here is the windows you can control the evolutionary algorithm in the EvoMass. So the first tab here is the input output. This one is let you to know how many input here. But because yesterday, like Francisco asked me that whether I can change here. So when I developed the SSIA, I plan to make this part can be editable. But I just later on I just have no time to do so. So I just keep here just like just leaves all the value here, but you can do nothing. Another thing is that you can see that because in this component we have a 7 unit meshes. So here we have 42 variable. However, if you change this number here, let's say that we can make the floor number a variable, let's say like a 15. So it means that they will increase or add one more variable in the design generation rather than just control all the box. We also need another extra parameter to control the floor number. So in this case, we take a look on it. We can see that they will have one more variable will be added here. So for the moment, they have 33 variable in the design generation component. And the other thing is that in this version of the EvoMass, you are actually technically you can combine 2 or 3 components here. So you can also add another, if let's say you have 2 buildings to be evolved simultaneously, so you can use this function to generate the 2 building geometry and then to connect both of the component or the 3 component to the optimization algorithm component. And in that case, you can also see they will have another component will be added on this list. So you can check the number of the variable in these 2 components. But just remember that when you add one more component, it means that they will add a large number of the variable here. So if there are too many variables for the optimization algorithm to change or to control, it may introduce some kinds of the search difficulty for the optimization algorithm. Because if they're just like I said, the design space or the search space is a multi-dimensional design space. One more variable will add one more dimensions in the design space. So if you add another component, it means that like this, in this case, another 42 dimension into the design space. So it will create a huge search difficulty for the optimization algorithm. So when you're using like a 2 or 3 components in the design generation, maybe you can also decrease the number here to make the optimization, make the line of the optimization algorithm a little bit easier. So if we decrease the number here, so you can see the overall number will be also decreased. So it will be facilitate the optimization algorithm to identify more accurate result for the designer. But in this case, we just using one generated component rather than 2. All right, we go back to here, and here is the input, and in the output, you can define the direction of the optimization. Let's say here is the maximize, and you can also change it to the minimize, depends on what evolutionary direction you want to be. Sorry. And after you finish this part of the setting, you can go to the SSIEA. So the SSIEA is here, you can have some parameter you can set. The first one is the number of the subpopulation. So if you remember yesterday slide, the number of the subpopulation means that how many of this circle will be. Let's say if you only have a 3, so there will only have a 3 search process that can focus on 3 regions. But if you have a 5, they can cover more design spaces, regions in the whole design space. And the size of the subpopulation means how many design or how many individuals, if you're using the evolutionary optimization term, in one of this subpopulation. And the termination threshold is how many generations the evolutionary process will go through. And the mutation rate here is that you can set 2, but because the mutation is like the random shuffling on the design, it means that at the beginning of the optimization, maybe we would like to have a higher chance have the random shuffle or the random variation in the design population to explore other unknown design regions in the design space. But in the later part or the stage very close to the termination of the optimization process, we would like to decrease the mutation rate, because I guess in that case there will not many region need to be explored by the whole design population. So it means that we can more focus on the design the design region we are already the subpopulation already focused on. Just like here, let's say this largest circle is the first generation of the design. In this case, we can still allow some of the design this population to explore the region like in here or here. But in the last generation, we said that we are already explore all these regions, so we just focus on the regions or the very small area in this region. So this is the implication of the mutation rate from the design space perspective. But if you are just using the mutation radius decay is none, it means that they're just using this one. And you can also change it to linear. It means that they will decrease from the 0.35 to the 0.1 along with the whole design optimization process. Or you can also using the exponential one that this can decrease to increase the decrease rate of the mutation rate. So, but usually you don't need to worry about that. If you have you don't really care about the very subtle difference between the optimization result. You can just using the null. It's okay. And the migration rate means that because they have a several subpopulation, it means that some kind in some cases, maybe one of the subpopulation reached the convergence very early in the whole compared to other design subpopulation. So in that case, they can exchange some of the individual among this subpopulation and to see that whether this new individual can bring in some new genotype into this subpopulation and try to help this subpopulation to get rid of the convergence on this region. And the tournament size is about how to say, is the just a very basic operation in the evolutionary algorithm is that they will select, let's say in this case, they will randomly select 10 design from the 30 design in the subpopulation as the basis to use this individual as the parents to reproduce the offspring for the next generation. But this is not to say that we just directly using the 10 design. We still need to have a tournament selection rate, tournament selection. It means that firstly, we will randomly select 10 design from the 30, and then we will select the because here is a 0.5 is not very accurate. Usually, if you set the 0.5, it will go to the 0.6. So it means that they will select the best 60% of the design individual from this 10 design as the parent for the reproduction. The detail of the reason why we're using this kind of the tournament selection is you can find in some paper about the evolutionary algorithm, or you can just check the paper I write for the SSIEA, so they can have some more explanation of how this algorithm works. All right, I guess this is the whole. So, and here also have an normal Louding hypercube sampling. This is just using the Louding hypercube sampling to make the initial generation of the design can be more evenly separate on the whole design space. But usually they will compute a little more. They will use a little bit more computing time. So usually I won't enable this. And the k-means clustering is that because we're using we will divide the whole design population into let's say like a 5 subpopulation. So it means that if you don't need the k-means clustering, the 5 subpopulation just randomly to pick let's say the 30 design from the whole the whole design population of the initial generation. Because here is 5, here is 30, it means that the initial population is like 150 design, and then after the first initial generation, each of the subpopulation will randomly pick one of the design, pick 30 design from this 150 design. But if using the k-means clustering, they will just each of the design subpopulation just pick the design very close to each other. So it can means that this actually can help to separate the design subpopulation on the design space, rather than, because if you just randomly pick, maybe you can pick like a 1 here and 1 in here. So it's still quite not very focused on this region. But if using the k-means clustering, they can force the design subpopulation to focus on the a more confined region in the whole design space. So the auto run is you don't need to worry about, because it's just using some like a research purpose that can keep the optimization process to run several times, but you don't need to use that. So after you finish the setting here, you will get the total number of the iteration. The iteration is not the generation. Iteration means that how many design will be generated and evaluated in the whole design process. So here have a 100 generation, and with this setting, you can see that we have overall 3,150 iteration for the whole design process. And we change here. You can see they will change accordingly. So you can using this to evaluate how long of the optimization process will be run based on your current setting. So I will show you a very fast optimization process using this method, but just very fast. So we try to keep the number a little bit small. I guess 400 is all right, maybe. Not sure how long. I guess it should be quite fast, maybe like 10 minutes to finish. And the other thing is that if you when you start your running the optimization, you need to restore the whole GH file somewhere on your computer. Let's say here, this GH file is saved in this direction, in this folder. After the optimization start, the component will create automatically create some backup file for you. I will explain it later to you. And so we can start right now. So there we have a table post up, and also have a timing here to calculate to record how many time we use for the optimization. So I guess we will finish the optimization quite fast. So the backup file will be created after the first generation finish. So if let's say, because in my previous experience, usually like your computer suddenly shut down or there's some power failure, the whole data you already have collected by the optimization algorithm, optimization process will be all lost. So using this function, you can, let's say, you don't need to worry about your loss or your data of the optimization, because they will recall the component will help you to do the backup here. Just like here, they will create the backup folder. So here you can see the GH file is already saved up and will be restored again. And here is the setup file for the generated component. And here have a they will create one backup file for each generation. So you can see that if we have like 10 or 20 generation, they will create 20 of this backup file with the XML format. And we can wait a little bit to let the optimization process to finish. So while we are waiting for the optimization, maybe you have any question about this part. And here you can ask. And also during your run optimization, if you like, you can also click this button to show some diagram for you. For example, the improvement will show you the improvement solution, or you can see the fitness progress trend line based on the improvement solution. You can find how the optimization process so far to find the best solution, and how the best solution, how each of the improvement solution in the whole design process. And the color of this line indicate the different subpopulation. It means that like the purple line, it means that all these designs for one subpopulation. The red line is another subpopulation. And you can see that for so far, all the improvement solution is founded by this subpopulation with the purple line. And the other 4 subpopulation cannot find very good solution, except for this green one. They have one on here. And all right, and also you can using this information. The information also have some of course information about the optimization process. The thin line means the average fitness of each of the subpopulation. So you can see that they are they will gradually increase with along with the optimization process. this SIG line is indicate the standard deviation of the fitness in each of the subpopulation. This can use as an indicator as the how difference of the design in each of the design subpopulation. So if this curve goes down very low, you can see that all these design have a similar fitness. And in other words, maybe all these design will look similar. And if this curve is still quite flat, it means that there's still many different design in the design subpopulation. It means that the whole design population may not converge very well in the optimization process. And I can show you some more sensible of this slide here. So here is the fitness progress trend line for design optimization process with a longer run. You can see that the SIG line, the standard deviation, will be decreased gradually, and in reverse, you can see that the fitness trend line will be goes up. And you can still find some information here. For example, in this green line, you can see they suddenly have a very large leap in this area. So it means that maybe for this optimization process, and for this design subpopulation, it suddenly find a very good solution. So you can also see that the average fitness also have a very great leap here. So this can help you to understand the whole the behavior of each of the design subpopulation. So you can see that in this optimization, the blue one have a very good converged trend line, and you can see the green one is actually very inferior at the first half of the optimization process, and suddenly find some good high performance design, and then they will goes up very fast and surpass the other three subpopulation. And for the other three subpopulation, they are just in between the blue line and the green line. So you can use this trend line to find some interesting thing in the optimization. But if you are not very interested in the optimization itself, you just can ignore them. And the other thing is like this one is also the improvement trend line here. You can see that the green line just very goes very fast after the first half of the optimization process. So you can just connect this information together to try to understand the whole design design process. So here it is already finished of the whole design optimization process, because we're just using a very small number of the generation. So we can see that actually the optimization is still not reached convergence, and you can see the standard deviation is still very high. So it means that the design in the design subpopulation is still quite different from one and another. And after we finish the whole design optimization process, we can also regenerate the design in the whole design population. Firstly, usually when you start to analyze the whole optimization result, other than you just using this diagram or another diagram, I forget to say that here you can have the distribution. Here using the parallel coordinate to see the distribution of the value of each of the genotype. You see that here have 42 parameters here, and the last two one is the fitness. So you can use to see whether here have some kinds of the pattern in the genotype level, but it looks like in most cases, I cannot find a very clear pattern in using this diagram. So I never use this in my research or my design. And the other, when you finish the optimization, let's say another function I can show you is that you just close it, and let's say this is the second time you open this GH file, and then you can open double click here, and here is the SSIEA. You can load the project, and you can find the backup file and to restore your whole design optimization process using this function. Because this have only 600 designs, so the loading speed is quite fast. But if you have, let's say you have an optimization process with like a 3,000 design, maybe this can cost like a 1 minute. So just don't panic if these windows do not pop up. And after you restore or reload or your whole project, you can first using the show the current population, which means that they only show the design in the final design population, and to not show the design excluded by the optimization process. And show the fitness first. You can make the fitness goes to in the beginning of this table, and you can click here to sort the whole table and to make the good fitness the design with a good fitness on the top of this list. So you can see that the 100% is a relative value to help you to indicate or understand what is the precision of design in the whole design process. So this overall fitness is just to let you know the relative performance of design in this design population. So you cannot to compare this design with the 100% design to compare to the other 100% design generated by the other optimization process, because this is just the relative value, is not the absolute value. The fitness one here is the absolute value. It is like in here is the sunlight hour for us, and also include the punishment function on the gauge area. So we can select this one, and then to right click our mouse, and then to generate the model, so we can reinstate the best design found by the optimization process. And then you can do like a screenshot, and or also bake the whole geometry, and to do another round of the like a visualization or analyze. So each of the red one means that this is the design. This is the best design in in one subpopulation. So usually when I try to analyze the result of the optimization, I only focus on this red one, because let's say this free white one between these two red, it means that this free one maybe comes from the same subpopulation. It is easier to say, let's say the running index 444, you can see that they have the same number of the variable one. So it means that these two maybe comes from the same subpopulation. So if you analyze these two one, you will find these two one maybe look quite similar. But in this stage, because the whole design optimization is not reached the convergence, so this still look quite different. But if you run like a 3,000 optimization or a 5,000 optimization, these two one maybe look very similar. So you don't need to put more too much focus on the design with very with great similarity. You just focus on the differences between the added design from each of the subpopulation. And also here have some design with the blue. The blue one is means that the improvement solution. So here you can find the connection. Let's say the running index means that this is the position or the time or how many design before or before this one has been generated during the whole design optimization process. This can be correspond with this diagram. You can see that usually the 27 maybe just this one, and 16 maybe this one, 27 maybe this one, and 165 maybe here or maybe here. So this is the improvement solution. So you can also use the filter to only show the improvement solution. Improvement solution, you can see how the design will be evolved during the whole design process, from the performance with like a 77% goes up to the 85, and then to go to the 100%. So you can see the design evolution process using this function. Okay, I guess this is the whole thing about the optimization part. So any question about this part? Now you can ask. If we do not have any additional questions, so I guess we can have a small break here, like a 10. Sorry.
Yeah, no questions for the moment. Thank you very much. Actually, I did miss the selection of the option to save the data in the backup folder, but actually then I think I found this autosave option, right? I mean, to set the automatic saving of the backup files. What is the setting?
Sorry, can you say again? No.
Yeah, sorry. I was asking which is the setting to automatically save the backup of the population data?
Yeah. So you mean where this data will be saved, right?
No, where you say to save the data in the optimization software interface?
Where to? Or you don't need to save the data because the data will be saved automatically.
Okay, because actually when I started the optimization, it was not saving. And then I just clicked on the autosave option, and then when the process starts, yeah, you see in the right lower corner.
Yeah.
After I click there, then the autosave started. Otherwise, without that checked, didn't start automatically.
Actually,
So I thought I missed, in fact. But in your case, was saving without checking this option, I understand.
Yeah, you don't need to check this. Honestly, I also do not remember why I put this autosave. The autosave here is because in some cases, if you are using the auto run, I guess they will have an autosave. Because the auto run, it means that if you want to do some research, like we run the optimization like a file type to see whether we can get a stable result, you can enable the auto run, and then they will have autosave. But because the autosave is is a function I implement very early in the SSIA before I implement the backup function. So the autosave may be a little bit useless for this for the moment. And the autosave have maybe like if you're using the auto run, like a run a several times, they will create different folder to save the result based on each of the run of the optimization. So if you are, let's say you click the auto run, let's say if the optimization restart again to run the second time, they will replace the backup file here. So, but if you maybe like using the auto save, they will create a folder to restore the data of the optimization to separate the data between among each of the optimization run. But I guess you just don't need to click here, just let them to run, and then you can have the backup file here. And when you finish, you just copy the backup file somewhere else for the future use.
Okay, thank you.
Oh, no problem. All right, if we do not have any other question, we can have like a 10 minutes break and we'll see you in 10. All right. Try to finish design using the EvoMass. So in this case, we can go through some of the previous example to see to understand how the EvoMass can be applied to the design process. And before showing the example or the case study, I will also have one more slide about the organization part. This is some diagram on the paper about the SSIEA, and you can see there have some comparison or some schematical comparison between the behavior of different evolutionary algorithms. So the first one here on the top left corner is the single objective optimization algorithm, like the genetic algorithm. So they usually just focus on the best solution in the whole design space, but usually for example, the standard genetic algorithm is not very efficient. So they cannot ensure that each of the optimization can find a very good solution. Sometimes the optimal solution they find may be just like the design in here. Let's see, we can draw something on that. Can draw anything. Okay, and the middle one is more like multi-objective optimization. Usually, if you are familiar with the multi-objective optimization, you know some terms like a Pareto optimization or the Pareto forms. So it means that they will try to find a set of design solutions that do not dominate by one and another. It means that let's say have two performance, and for each of the design in the Pareto form, the increase or the decrease of one performance will also incur the opposite direction for the other performance. Let's say if you increase the solar irradiation, it may be also increase the discomfort glare. So this kind of the thing is like the Pareto optimization, and this one is the last one is the purpose of running the of the development of the SSIEA. They try to using the single objective optimization, but try to make the optimization result have a higher design diversity. So to compare with the single objective optimization, like a standard genetic algorithm, they can provide higher diversity. But compared with the multi-objective optimization, they can tend to provide a solution more focused on the design, have the excellent overall performance, rather than like the multi-objective optimization. They try to find too many solutions, and sometimes you analyzing this solution can be very it's very tired and also time consuming. And the second line of this diagram is show that the relationship between the number of subpopulation when you're using the SSIEA. When you use the but this have a condition is that you're using the same iteration number. Just remember it's the iteration number, not the generation number. So the overall of the design generation and evaluation is the same. So if you only have the two design subpopulation, it means that each of the design subpopulation will have a more resources, computational resources to search the whole region. It means that they can find a very good solution in the whole design space. But if you, let's say, have a 5 design subpopulation, they will try to, because each of the subpopulation will have a relatively limited computational resources to search for the high performing solution. So you can see that for each of the subpopulation, the search efficiency will be decreased. So it results, it will cause the result, it will to make the optimization result only to may not able to find the best solution in the whole design space, but they can in turn to increase the diversity of the optimization result. And when you further increase the number of subpopulation, it will be more difficult for each of the subpopulation to find a very high performing solution, but they will further increase the diversity of the optimization result. You can see that the expected fitness level will be decreased when you increase the number of the subpopulation. So this is the trade-off between the number of the subpopulation and the trade-off between the diversity and the quality of the performance of the fitness of the optimization result when you're using the SSIE, especially when you change the number of subpopulation. So this is some kinds of the maybe easier for you to understand the idea behind the SSIE. So we will move on to some example of using the EvoMass in the architecture design. So they will, let's say they have a 3 different, for the moment, I can say that I find 3 different ways for the designer to use the EvoMass in their design. So they can categorize as the design synthesis, design exploration, and design abstraction. So for the design synthesis, it means that the designer can use the optimization result and try to combine it to create a design using the result, using the optimization, the design in the optimization result. So like this one, here is a educational building design, and there is a team of students using EvoMass in the early stage design exploration. So they respectively conduct 4 optimization process, 2 using the additive massing and the 2 using the subtractive massing. And the other, on the other hand, is that they will also run the 2 set of the optimization focus on the different objectives. So one objective is the daylighting, and the other objective is the solar irradiation. And after that, they also find some general tendency in the optimization result. For example, they find like the building will typically have a street shade in the floor plan, or also have a courtyard in the center of the building if they are focused on the daylighting. And they will and then they find that the building have like the step value, or also the self shading if the optimization is focused on the solar irradiation. So but they find that also the result, the design in the optimization result is quite how to say, is have a very strong tendency just mentioned above, and they are maybe not very architectural interesting. So they're using a multi-objective optimization to try to run an optimization to combine the 2 objectives, and then the purpose is that they try to dial down or try to decrease the intensity of the feature, like the courtyard or the step volume, and also try to, let's see whether the optimization can find some design to combine this strategy. So after they run the optimization, they select one of the design that quite architecturally interesting and also present the features they find in the previous design exploration. But as the multi-objective optimization cannot have a very strong tendency, so they can still using the knowledge extracted from this part to intensify on the building design in some local part of the design. For example, they find the step volume, so they use this strategy in this part of the massing, and to also create some step volume on the on this area facing to the courtyard. So in this way, they try to synthesize the whole building by combine the optimization result they collected in their previous their previous optimization process. And this is another one because this one is also just design the design the user conducted in a 5 days workshop. So the completeness of the design is not that good, but you can see that they are using the EvoMass in context of the vernacular building typology and also a very traditional city in the Iran. And then they respectively running the optimization based on the subtractive and the additive component, and also focus on the sunlight hour and the solar irradiation, just like I taught yesterday. And they respectively running this optimization and try to collect some information from the optimization result. And also they find some interesting thing is like if using the subtractive one, they can find that the result is quite similar to the vernacular building with the courtyard in the center or the very narrow alley, because this can create some kinds of the cell shading effect for the buildings. But when they using the additive one, they find that they are also the result typically have a very large overhanging structure, and also because and this overhanging structure also lead to the cell shading effect. But they further focus on the difference between the result. They find that maybe the traditional courtyard building maybe is subject to the structural constraint, because in the ancient time maybe it is not very easy to build a very large overhanging structure using the traditional building material and the structural method. But in the modern time, if we are allowed to have some kinds of the very large overhanging structure, maybe it is more efficient to create the cell shading building and to achieve a better passive cooling effect in this area. And finally, they try to combine all the features they found in the design and try to synthesize into a one building design. And but they are using this design just manually to add all the features they find in the previous optimization result. But they still have some kinds of limitation, like the building is still the final design is still like a box-shaped building, so they do not introduce other kinds of like the curve or the freeform geometry in the building design. And also they do not do another like a post evaluation of the design, the building they design using the previous optimization result to evaluate whether this approach is efficient to create a design with excellent building performance. But if you just consider they have only 5 days to do the design, so this maybe if they can have more time, they can conduct this part of the comparison study and to further to improve the performance of the design. So this is another example is conducted by the student in my university, and this is a little bit different from the previous 2 examples. So in this example, they are keep using the EvoMass and also try to navigate the optimization process to find some solution that can both have a very good building performance, also can satisfy some design intent defined by the designer. So this is like a commercial complex with some office building and also some like the gala and also some coffee shop, some kind of this thing. And at the beginning, they only focus their optimization on the building performance, like a daylighting, and also the sunlight obstruction to the public park on the north of the building. They try to minimize the sunlight obstruction to the public park and also to maximize the daylight accessibility of the building. And after they finish the first round of the optimization, they find the design generated by the optimization is quite boring, but I cannot show this design because they do not do a very organized documentation. And then they try to include some design intent into the optimization process, into the fitness evaluation function, just like I said in the previous section. Firstly, they try to create more rooftop area for the user to use as some kinds of semi-outdoor space to viewing or some kinds of the casual event. So they to calculate the number of the roof surface, and then using this as a wall function. It means that if the design have a more roof surface, they will have a higher fitness and will be more favorable, or to have a higher chance to be survived in the following optimization process. So you can see the design typically have a very sparse building meshing and have many rooftop surface. And the second one is that they also want to create a entrance area, also a semi-outdoor area for the entrance space. So in this part, they try to define a volume here as their potential space for the entrance, but they do not just clear cut the whole building in this, because if they have a very clear box in this entrance, the building maybe looks a little bit boring. So they just define a volume here and try to calculate the overlapping area between the generated building and this volume, and using the percentage of the overlapping area to this volume as the penalty function. And then if the building have a very large overlapping area with this volume, the building will have a very low fitness, and then will be may not able to be survived in the following optimization process. And so using this way, they can gradually to make the design view to have some kinds of this semi-outdoor space in their in the optimization result. So other than these two quite critical factor, they also include like the density of the floor area, the whole building ground floor, and also some other kinds of like the FAR into the whole optimization process, and they get the final design like this one. And you can see that the design not only to satisfy their need, they have many rooftop area, and also this entrance space. They also have a very clear performance implication reviewed by this design. So the first thing is that because the building the designer want the building have a very good daylight accessibility. So you can see that all the meshing have a very narrow floor plan. It means that they can prevent the negative they can avoid the disadvantage of the deep plan floor building, that the central part of the building usually have no nature daylight accessibility. And the second one is that in this corner, the building have a very low will decrease their height, so they can allow more sunlight to reach the public part. But in this part, because they already have some like a high-rise residential tower, so no matter how this building change in this part, the shadow caused by this building will still have a great impact on the whole on the public park. So so they just make this advantage, and then to occupy the whole space on this corner, and to try to make more space for this corner to decrease the negative impact on the the sunlight accessibility for the public park in this design. So since we are talking to this case study, I can also I think maybe also relevant to talk about some kinds of the why we use the punishment or the award function in the evolutionary optimization. So the punishment of the award function, you can understand like some kinds of the soft constraint. And so in comparison, there are also another kind of the method called a hard constraint. And also there's some like a reviewer sometimes have some suggestions like why you don't just using the hard constraint to eliminate all the design that not satisfy your requirement, the requirement defined by the designer. The reason is like this. If you're using a hard constraint like this way, here is an example that the building try to avoid occupy the space of the tree. So if this design is have a very good performance, but they occupy the area, the space, or they invade the space divided by the tree. If we're using the hard constraint, we can just give them a very low fitness or very high fitness. Depends on the organization direction just reset in the previous section, and then this design will be directly killed in the evolution in the following evolutionary process. And even though the genotype of this design or the parameter of the design can lead to some high performing design because this one is killed, so the whole genotype or the parameter of this design will be lost in the whole design population. But if we're using the soft constraint in this case, let's say the performance is 900 and the punishment is 0.6 because they have still have a very large overlapping area with the tree. So we get the final fitness like 540. And then this design can, because this design, we do not directly kill them, we still allow this design to be survived in the design population. So this is possible for this design to be to recombine their genotype with other design, or we using the term, the evolutionary term called the crossover with other design, and then to create a offspring design that have a less overlapping area with the tree. And in that case, maybe the design have a certain kinds of the reduction in the performance, like say have a 100 reduction and the performance goes to the 800. And then, but the punishment will be also decreased from the 0.6 to 0.75. And then the overall fitness can still increase a little bit compared to this one. And after maybe several generation and combined with other design again, maybe they can reach a design that can only have a very small portion of the overlap with the tree area. But of course, the performance may be further decreased, but the punishment will also decrease. So we can get a better design compared to the previous two. So if we're using the soft constraint in this way, you can navigate the whole design population, design organization process to find the solution that can satisfy your design requirement rather than using this one, maybe because using this one, you will lose many potential design that can lead to the high performing solution during the whole organization process. So here is the paper describe this this case. Here also the paper shows how the design the student using the soft constraint in their design. At the beginning, they only have a very simple fitness with one SDA is the daylighting performance with maybe some penalty, the punishment function on the area, and then they try to add their a wall and punish function on their fitness and try and finally to navigate the whole organization process to toward the design direction they want. And this is another example of the design exploration. This also I show you this slide yesterday that the one of the student using the EvoMass in the early stage design exploration. So just like in this workshop, I do not ask the student to use the organization part immediately at their design process, but they try to using the random sampling thing to do the massing and the size study and to try to combine with other different types of the simulation tool like FFD or the the sunlight hour or also the solar irradiation and daylighting. And they try to, the student can find some hidden connection between the building geometry and the performance. So after the student do a several iteration of the design exploration, the student can have a basic understanding of which performance factor is more important for this design test, and then to formulate optimization function for and run the optimization. So in the final optimization, the student think that I need to have a good daylighting for this high-rise tower, but also try to decrease the sunlight obstruction for the surrounding building, especially this high-rise building. So in other words, is that to increase the daylighting performance of this target building, and also increase the sunlight hour of this the high-rise building on its norm. So the student run the optimization and then to get the final result like this one. So you can still see a very clear architecture implication related to the building performance. So the whole building still have the major part of the building is still have a very narrow floor plan. So it ensures that the indoor space of the building can have a good daylight accessibility. And they only have a very large block here and cast some shadow on the ground. But the other smaller box on the block of the building will all hiding in the shadow casted by this large building block. And if you have some experience in the passive design, you may familiar with a strategy called the solar envelope. So this kind of the design is also in agreement with the strategy of the solar envelope. So they try to using the building meshing to decrease the overall context shading caused by this by its building geometry, and try to decrease the negative impact on the whole surrounding building. So this one is actually not the design, but it's a research, also the paper. I will present it tomorrow on this conference. In this research, we combine the EvoMass with FFD simulation. It's a fast fluid dynamic simulation, and also the sunlight hour. But another thing we also explore in this paper is that while I said that the EvoMass can create a design space with a diverse design solution, but actually the design parameter defined by the designer can also have a great impact on the design generation and also on the design optimization. So in this case, we try to explore how this design parameter can affect the design optimization result. So here we envisage 3 types of the building meshing, and we're using the parameter to control the design generation to reflect this type, these 3 different building typology. The first type is the more bulky building geometry. So in this case, we have a 4 mesh element, but each one will have a very large volume. And this one is have a 6 mesh element, but each will have a smaller size constraint. So you can compare that each of the box will become smaller. And this one have a mesh unit, but have a more the size constraint will is further decreased. So you can see that this one is more sparse and more like the Vauxhall building, and this one is more like a very bulky building. So if we're using these 3 different parameter and run the optimization, we can see how this parameter can change the result of the optimization. So when we finish the optimization, we can see that for the wind speed, we can see that the design with a large mass volume usually have a smaller wind shadow area, but for the design have a smaller volume. You can see that because the wind can still cause the between the gap of this small volume, so they can also reduce the wind shadow area. But for the sunlight hour, most of the design with the large block mass, they will lay down on the floor and just spouse on the floor, so they can decrease their shadow casting on the floor. But for the smaller one, you can find that the implication is quite similar to the high-rise building. They can use the solar envelope approach to to reduce the overall shading on the ground. So you can compare this the whole sunlight hour on this diagram. You can see that the larger one usually have a very small shadow, but this smaller one usually have a very large shadow, but just focus on some area. But the dark area, the black and the dark blue area of this smaller one is actually quite small, is smaller than the this area created by this large building mass. And here is another example that one of the student is the master student from Taiwan using the EvoMass in her research. But in here is a quite interesting example, is that the student conducted research based on design. It is a design that proposed by architects. The architects first proposed 3 different design strategies, like a tube, yard, and parcel, and to indicate different building typology. And then the student using the EvoMass using the parameter also combine the soft constraint to represent these different types of the design strategy or the design concept, and then run the optimization. So in that case, it means that you can use EvoMass to repeatedly to represent different types of the building design typology or design intents, and then to run the performance-based design optimization to see which design concept or the design direction can have a better overall building performance, and which one may have some hidden or latent disadvantage for the building performance. So this is a little bit different from the previous example. The previous example is that you will formulate your own design problem and to propose your design idea based along with the optimization process. But this one, you first to come up with your own design concept, and then to run the optimization to compare which concept is better in terms of the building performance. But the advantage here is that if you do not use the EvoMass, you need to build up 3 different parameter model. This can be quite time consuming, but using EvoMass, you need to change some parameter and some soft constraint. You can redefine the whole design optimization workflow and to generate the kind of the building you want to. And here is the another very interesting example is that this is actually not a design, it's a research that combine the building massing design and the facade design. So we using the some cell adaptive algorithm to generate the building facade. For example, we first let's say to see this animation. First, we generate the building massing, and then we run the solar irradiation simulation. And based on the solar irradiation on the surface of the building, we define for example, the density of the shading device or the window to wall ratio based on the solar irradiation intensity. So this is kind of the cell adaptive algorithm. So based on this cell adaptive algorithm, we generate a building with a facade pattern, and then we analyze evaluate the building performance on the daylighting, because the facade with different shading device and or the different floor to windows to floor wall ratio can have some kinds of the negative effect on the daylighting quality. So using this approach, we can to combine the facade and the building meshing for the optimization. And the other thing is that because if you're also using the parametric model to define the facade, then we have a large number of the parameter, because maybe you need to define the parameter for each of the windows or on each piece of the facade surface. So this is make the optimization impossible to be solved by the optimization algorithm. So using this way, you can avoid the problem of using the conventional parametric model to generate the facade component, but you can just using this cell adaptive algorithm to generate the facade with different different patterns or the different density of the shading device on the surface of the building. And using this approach, you can see that the facade can reversely affect the whole design optimization process of the building meshing. Just see the diagram on the left-hand side. You can see that the first one is the facade using the vertical shading device. You can see that because this kind of the shading device is very good on reduce the solar heat gain for the indoor space. So most of the design can have a very can have a more compromise on the daylighting. So most of the design have a very shallow floor plan here. But for this one, the second facade scheme, we're using like just like a triangular facade surface shading device. This shading device we found based on the result of the optimization is a little bit weaker in the shading effect. So you can see that the whole building meshing will have a very large overhang structure to try to create some kinds of the cell shading effect. And the last one, we do not apply the shading device, but only change the window to wall ratio. So this kind of the approach is the weakness in the shading effect. So you can see that the design is not only have some kinds of the large overhang structure to create a cell shading, and so in some cases the building will be separated into two entities, and using one building as the shading device for the other building. So it's like the building on the south will cast the shadow and protect the building on the north to receive too many solar irradiation. So using this way, you can see the interrelationship between the building facade and the building meshing, and can make a more holistic understanding between the building performance when you come to different building design elements. And this one is this is another one. Sorry. It's also from the 5-day workshop in the middle of this year. And in this one, the designer, the user of the EvoMass is based on the Egypt, and he defined an objective function that they want to maximize the sunlight hour on the eastern facade, because maybe the sunlight on the morning maybe have a little bit a small amount of the solar radiation, and also can provide sufficient nature daylighting, some kinds of this reason. And the other thing is that he want to maximize the solar irradiation received by the roof surface to using it as and also install the PV panel for the to generate the electricity for the building. So he run the optimization based on the subtractive and the additive component, and get the result. And because this user do not have the time to finish the design, so I said that maybe you can try to using the try to find some real world design example based on the optimization result and some design precedents, and then just like this diagram this slide show that the designer can find some quite similar design reflect the same design strategy in the reality. But later on, I find that maybe this is the good way that help the designer when they're using the EvoMass, they can still get rid of the box, boxy volume generated by the EvoMass, because you finding some real world example, they may give you another different kinds of the inspiration from the architecture language, and then you first using the EvoMass to get the basic idea or the strategy of the high performance design, and then you get the and find the design precedents, and then you can also try to synthesize the information based on this design precedents, and also the information you collect from the organization to finish your design. But because there have some inspiration from the design precedent, you can still get rid of the orthogonal the box very box shape design generated by the EvoMass. And I guess this may be the last one. But the previous example, I'm still not very and not say that it is very successful to apply the EvoMass in the architecture design, because you can see that most of the designs still have like I said, have a very boxy geometry in their final design. So my idea or my intention of develop the EvoMass is still to support the designer to find some general design tendency, and then to translate this design tendency or the design information into their and combine with their own design language. For example, if like here, if you find some step volume, you can make up the you can propose a design more interesting in terms of the building geometry like this one, and also the cell shading. You can also change the building geometry to some kinds of the more with more your personal design intent or design language in the whole building geometry. And also like this solar envelope design, you can also change using this information or the general idea to create your own building geometry. But for the moment, there's still no student or user when they're using the EvoMass and can achieve that. But I still want to emphasize on this aspect, because this is actually the real purpose when I developed the EvoMass. Okay, I guess this is the final part of this section. There is some frequently asked question, and maybe just have a very fast discussion of this question. The first one is that whether the EvoMass can generate a curve for freeform geometry. The answer is no, but I'm also aware that actually if you can include some freeform geometry, they can also improve the performance of the building. So in this case, you can see that if you're using the boxy geometry to to generate a courtyard building, and using more geometrically more freedom approach to generate the courtyard, you can see there have a very large differences in terms of the performance. In this case, is the daylighting. But the idea is that you can use the EvoMass to get the first design, the courtyard one, and then you can develop your own parametric model that to introduce more geometrical freedom into the building geometry, and then to run another round of the optimization to find a more accurate result, more accurate design using this approach. And the second one is that it's possible to define as many mass units as I want, or the user want, or like a was, but it's actually, this is not very recommended. I also set the maximum number you can define when you're using the additive or the subtractive component. The reason is that there are many examples using like this voxel approach to generate the building massing design. I guess Francisco also have a paper using this way. But using this way, usually you cannot combine with the evolutionary optimization, because there will be too many parameters to control the whole building massing. So I also conduct some kinds of the research here, and the first one, the naive model, is try to mimic the way that if you just using one parameter to control one of the voxel and then to connect it to the optimization algorithm, we can find that firstly the design generator will be very chaotic, and then even we connect it to the optimization process, the optimization is actually cannot find a very high performance design, and the whole optimization process is more similar process that try to exclude the infeasible design from the design population rather than to find a high performance design. But if we're using some more constraint in the parametric model to regulate the whole geometry, so we can find that the optimization is more efficient to find a high performance solution, because the optimization algorithm do not need to worry about the infeasible solution in the design space. And the third question is about, is possible to connect the EvoMass to the energy consumption? I guess it can. I already noticed that there are some kinds of the software or the plugin called the AutoZoomer. They can create some kinds of the zooming on because the EvoMass do not generate any interior partition of the for the building design. So if you need to, let's say, but most of the energy consumption simulation, you need to define different zone, like for the AC, the air conditioning things. So using this approach, they can provide you a very simple way to do the zoning and then to run a quite approximate simulation for the energy consumption. But I never tried this way, so maybe this is if you want to use the EvoMass in the energy consumption, you can try this approach. Let's see whether it can to do the energy consumption simulation. And the first one, the last one is it is possible to define more than one objective in EvoMass. For the moment, SSIEA can handle two objectives if you connect it to two fitness value. So it means that the SSIEA can also do the multi-objective optimization. But the problem is that I'm still not very sure that the reason why the architects or many researchers in this computational design area to using the multi-objective optimization. So the more fundamental question is that the designer really want to have those Pareto form or the trade-off design, or they just want to have optimization result with higher design diversity? Because for me, if I am a designer, most cases I just focus on the design diversity. I want to have maybe 5 or 7 design all have the very good overall performance, rather than you just give me a bunch of the trade-off solution. On the other hand, you can see that usually if you run the multi-objective optimization, the result, the individual in the optimization result is quite, the number of them is quite large. So analyze this design can be also quite, cause some kinds of the cognitive overload. So I'll not say that it is not feasible to use the multi-objective optimization, but when the designer or the researcher really use the multi-objective optimization, maybe they need to consider first whether the multi-objective optimization is suitable for this design test or the design scenario, rather than just to using, because in the maybe 10 years ago, there is no way to run the optimization, the single objective optimization, to have the optimization result with higher design diversity. But the SSIEA can try to provide something in between the traditional single objective optimization and the multi-objective optimization, to provide the designer another option. They can run the single objective optimization and then to also have the optimization result with design diversity. So I guess this is all of my lecture today. And well, any question about this part?
Thank you very much for this very interesting presentation, Likai. Actually, I have a question about the optimization process that we have run before.
Oh, all right.
Basically, yeah, what I wanted to ask is, I understood that I could, let's say, generate the building massing that produced a certain performance. So one of the many iterations. But actually, I do not manage, let's say, I do not understand how I can generate that specific iteration or massing solution. Did I understand correctly that it is possible to regenerate one specific iteration or solution?
Yes, it is possible. When you, let's say, maybe I will show you here. You mean the specific solution generated by the automation? Can you regenerate that? Regenerate
yes.
this?
I understood that from your when you were explaining this before. I understood that this was possible.
Yeah. So let's say you reloaded the whole design project.
Yes.
And here you got the whole table, and you, let's say you may be interested in some of the design. Let's say this one.
Yes.
Let's see, where is the design? Okay, maybe something. Let's create the context first. I didn't. All right. So when you reloaded your whole project here, let's say you want to regenerate this one, you just right click here and to generate a model. So this is the same one generated during the automation process.
Okay, but actually I thought it was that the option, but I do not have this option activated. Like it is not, I cannot select on that generate model. Maybe I had to check one thick one, this option before to start the optimization.
Sorry, can you share your screen? Maybe I can take a look on your screen. Let me stop sharing.
Can you see?
Yes, I can see it.
Okay, I have also another question first, since I'm here. This purple is the optimal solution, right?
Yeah, the 100% one.
Yeah, with this means overall fitness, so 100%. Okay. And then you see, when I select one option, when I right click, there is no possibility to do any.
Okay, I never encountered this one. Maybe can you, if you right click the other column, the next column.
You mean
somewhere? Yeah,
I cannot. I can click only on the number, but I cannot click on nothing. If I go, let's say here.
Oh, I see that your automation is still running. You can see that the running time is still counting.
Okay. Actually,
stop solving.
Okay. Then it doesn't stop automatically when it reaches the maximum.
No. I guess maybe something stuck. The automation may be stuck somewhere. Maybe the simulation is just finished, didn't finish, so the automation is still waiting for the new fitness value.
Now I understand, because actually I didn't realize that the iterations were 675, but then here I have 604. So okay, then
yeah. Maybe you can. Sometimes there is some error that can. Here you can regenerate the design.
Okay, then thank you very much. And actually, okay, then this purple one, I lost the purple one. Yes, this one. This is the optimal solution, 100%. And what are these other red?
Sorry?
Solutions? This like pink. Why those are in pink color? These other solutions.
The pink color means this one is the best solution in this subpopulation. So if you have, let's say, free subpopulation, it means that they will have a free design with this pink color. You can also, can you see the only show current population? You can enable that right below the show fidelity first. There have another box you can check, the only show current population. Yeah, you can check this. And you can click the overall fitness to solve the whole table. You can click the overall fitness, the text. You just click the text. Click again. Yeah, this is also the same. You can see that all the pink color will be on the bottom or on the top of your table, because this is the one have the best fitness in each of the subpopulation. The reason why I label this one, because usually I just focus on this, maybe let's say 5 design, because they usually have quite large design differentiation between because they from different design subpopulations, so they are typically have a very large design differences. So if you just focus on this design, you can analyze why they are different and which is their overall their shared tendency. So have a better understanding, because the conventional genetic algorithm, if you're running like using the Galapagos, the final optimization the design population is usually a bunch of designs quite similar to each other, so you cannot get sufficient information from this kind of the optimization result. So this is the reason why I label this red design, and then so you focus at the beginning of your analysis, you can just focus on this pink one, and if let's say you are interested in some of this one, and then you can also you can see they have a display option, the island. You can select the island with this design. Can you see that the display option? Yeah, you can select one of the island with the design you like, and then in this island or this subpopulation, this design is quite similar to the design you're selecting. You can see that they are usually have a very similar parameter variables. You can see you can find.
Okay, that's clear.
All right.
Thank you very much.
No problem. Do we have other question about this part or the optimization part? If no, I guess we can have another 10 minutes break. And all right, so I will see you in 10 minutes.